In this video, I'm going to be going through Chapter 2, Preliminary Engineering Studies, so this is the Year 11 course for HSC Engineering Studies. And at the start of Chapter 2, we have a dot point that talks about the skills of the professional engineer. So they identify engineers as problem solvers, designers, communicators and project managers. And Copeland has a little bit in the book, but I just felt as though I could, had something that I could contribute. So I have written my own definitions here. So to start, I'm not going to read, but I'm going to try and summarize this concept. Okay, so the first thing is, what is an engineer? Well, because we talked about earlier that the term engineer comes from someone who builds siege engines like catapults. The term engineer is pretty loose. Right, so in New South Wales, legally anyone can call themselves can call themselves an engineer, at least at the moment. There is a national engineering register to be registered as an engineer, but it's not compulsory at this point, and it's not a legislated thing where only people who are on that register can call themselves engineers. Comparatively, you can't go around calling yourself an architect. It would probably be the best example. You have to be on the architecture register to call yourself an architect. Engineer, not the case, and that's probably because the anyway, I'm going to move on. Typically, when we talk about engineers, we're talking about people who are professional engineers. Engineers Australia would consider that to be someone who has they've completed a 4-year engineering degree. And then generally there's someone who's still working actively in the field. So there's an accreditation process, so for instance, there's a chartership. I did my chartership before I left, working professionally. Okay, so in the previous chapter, we talked about what is an engineer, how would we define what an engineer does? We would say that someone who uses science and mathematics to develop products, processes, and structures based on predicted outcomes, predicted conditions or behaviors for the maximum benefit of stakeholders. And I talked previously about how a stakeholder is anyone who has anything to do with the project. Now, sometimes some stakeholders might be very low importance, right? There's a building project going on near my house, and I get frustrated about the fact that the construction noise that starts at 7 a.m. on Sunday mornings. And I called the council and they said, yep, they're allowed to do that. So I'm a stakeholder because I'm affected by that project, but I'm pretty low importance. And I don't think that they're going to be too concerned that I'm upset by the construction noise on my Sunday morning. But a good engineer will consider all stakeholders and weigh up the relative importance of those stakeholders. So even though they might say, you know what, we're happy to have a few neighbors be upset about the construction noise, that's a necessary cost of us achieving our goals. Okay, so the next thing is they talk about problem solvers. And to say, well, what's a problem solver? We need a few other definitions. So people often seek out engineers because they have a problem, need, or opportunity. Any of you who do design and technology may have come across this terminology. So I define a problem, need, and opportunity as so. A problem is an unwelcome or harmful situation. I like to think of a flood, right? If your house is flooded, well, you would say that was an unwelcome or harmful situation, right? It might be dangerous and certainly not something that you would like. A need is something that is required to thrive. It's not something that's so a guy called Maslow, he talked about, well, what's a need and what's a want, right? Mick Jagger also wrote a song in similar concept. But the point is that for us to say, well, what we need to thrive. So we don't need electricity, but we need electricity to thrive, right? So are you with me? Okay, cool. An opportunity is a situation where action can be taken for a beneficial outcome. So the idea here is I often like to think of opportunities are usually, hey, we have a chance right now that we could make some money. Or, an opportunity could be more broad. It could be, hey, there's only 2 people in this accordion competition. If I enter this competition, no matter what, I'm going to come third, right? That would be an opportunity, right? From an engineering perspective, we can look at flooding as an example of a problem. And how do engineers prevent flooding? Well, they build dams, but they also do things like they build stormwater networks, and they require new homes to have detention tanks. Now, you may or may not be familiar with a comedian called Rodney Rude. I'll let you assume what caliber of comedy he does, well, or did. I don't know if he's an active comedian anymore. The point is, he lived in nearby here. He lived in Sutherland Shire Council, and when he built his house, it was much less developed than it is now. There was a lot more open space. There was a lot more, there was a lot less concrete, so water could naturally find its way into the water table. Whereas over the course of, say, 20, 30 years, a lot more residential construction happened, and the Shire, it got more concrete and more built up, and more of that natural space got covered up, so that when there was a heavy storm, a lot of the water that once would have flowed into just the dirt and into the eventually to rivers, it instead hit concrete and it flowed into Rodney Rude's house. Now, you can imagine that if you're an engineer at a council and you were choosing the list of people who you'd say, hey, who do you want to be flooded? Rodney Rude is going to be at the bottom of that list. Anyway, so he was very upset about the fact that his house flooded. And at the time, his house had sufficient stormwater drainage, but circumstances changed as more and more development happened. And now what we do to prevent that sort of flooding is that new development must have tanks that can hold stormwater, so that if there is flooding, it doesn't end up flooding a prominent comedian's house, so that they can make fun of you on a global scale. So, okay, in terms of need, I used the example earlier of electricity. We all consider electricity to be an essential thing to thrive in our society. You are legally entitled, if you build a house, you are legally entitled, or I remember I used this to get electricity connected to my house. All properties in Australia are entitled to electricity as like a basic need. And people make the claim now that really the internet is really approaching that as something that's an essential service. Water is a similar thing, where we kind of consider access to clean running water as an essential part of our lives. Now, definitely people can live without electricity. I like to use this as an example that in the other class I went into some detail talking about a woman, Mouseheart, and she wrote a book where she lived for a year without electricity, made her kids do it too. And she talked about, the what that was like. But the fact is that for me, I don't know what my electricity costs. Let's call it $2 a day, right? Now, I don't live alone, so I share my house with 3 other people. So really, it's 50 cents a day for me. But if someone said to me, hey, you need to put $2 into a jar in order for the lights to turn on, I would pay that $2, and I would consider it a bargain. So I really think that even though people complain about the rising cost of electricity, when you think about what it is, it's just amazing. It's just incredible. Like, we're just so dependent on electricity. Forget the internet. I mean, there's no internet without electricity. Anyway, so in South Australia, they had a problem because they went very big into green energy. They had a lot of wind farms. The problem is they had trouble storing the energy produced by the wind farms, and then they'd have brownouts where certain suburbs would lose access to electricity. Anyway, they resolved this by getting Tesla to build a giant mega factory, and now they solved that problem. There was a problem where we needed more reliable electricity, and they solved it. What was the other example? Okay, so the other examples I had is that you might say, okay, so companies, they might say, we need to produce this many sets of headphones in order to make money. This is in order to not have to start firing staff. This is the amount that we need to produce. And that could be their need. And they might ask an engineer to say, can you help design factory equipment to help us produce that quantity? Or you might have someone who says, a farmer, for instance, they might say, we need a broadcast tower that can reach everywhere on our farm. So the broadcast tower, it's going to need to reach 2 k's away. So that might be their need. That's what they've identified as a requirement. Okay, engineers typically focus on where an organization can gain a financial advantage by delivering or an innovative technology or developing an innovative technology. Okay, so the big areas of growth in the decade of the 2020s is really alternative energy and artificial intelligence. These are what the biggest companies in the world, so this is what your Facebooks and your Teslas, or rather, what Elon Musk's various companies or Amazon are all working towards. They're all working towards alternative energy and artificial intelligence. These are going to be the things that decide this decade. I've heard enough from people I think that are smart to say that the 2030s, they're going to be dominated by space exploration, by satellites, and possibly even mining, space mining. I don't know how, it's outside of my field of expertise, so take it with a grain of salt. But, I mean, SpaceX is a company that's based on space exploration. That's another Elon Musk company. But Amazon and many other companies are all investing billions of dollars into what will probably be $1 trillion industry. It's just a matter of when. Other areas are really important are automation and biomedical innovation. And it's worth pointing out that often an opportunity could be just doing something slightly better. If you can, so in the case of, like, say, drink cans, if you can make a drink can 1% lighter, that's a massive saving when you're selling 1 billion cans a year. Okay. So to solve these problems, engineers have to employ a design process. So what are they going to do? They're going to identify the requirements of all the stakeholders. Now, like I said, some stakeholders you might say aren't very important, and you might not weight their requirements that highly, but you should still be aware of what their requirements are. So requirements are the things that the thing needs to do, the minimum standard that things need to address. Sometimes in design, I talk about things like people don't want cars, they want transport. So theoretically, if I produced a racing snail, if I bred racing snails that were faster, more fuel efficient, they didn't need to be parked, that they were safer, people might consider that maybe they would opt for racing snails instead of cars. I say that because it's a ridiculous scenario, but the thing is, people will often say, what does a car need? And they'll say, oh, it needs 4 wheels. Car doesn't need 4 wheels. What if I told you I could give you a car that was just as safe, but it had 3 wheels? Just as fast, just as fuel efficient, but it had 3 wheels, right? I don't really care how many wheels are on the car, right? People might say, well, a car has a steering wheel or an engine. Well, no, there are cars these days that are built that have neither of those things. They might have an electric motor and they might just have a computer panel. So that's an example of, only having what is actually a requirement and not ignoring everything else. Limitations are the extent of, say, well, okay, a racing snail that's 10 meters tall, well, that's not going to be viable because it needs to be something I can park. It needs to be something that can be stored reasonably. Okay, so we use something called the design process, and I have explained the design process as 3 main steps. You identify requirements and limitations, and then you develop solutions that meet those requirements, and then you evaluate those solutions. And ideally, you evaluate those solutions all the way through, right from the beginning until you get to the end, and then you say, okay, we finished our project. How well did we do? Can we make the next one better? And continually evaluate. Okay, we talked about why we want to collaborate last chapter, but we might collaborate because we can so the more people who are working on the project, we get more perspectives, we get more expertise, and we can just have a better output. We can, more people can produce more things. Okay, compared to other design professions, engineers have very strict standards. So, for example, bridges have to comply with the AS 5100. And if you don't comply with that standard, so usually, so for instance, if you're building a bridge for the government will require, they'll say in the contract that your bridge must comply with this standard. And if you don't, they can sue you in a civil court. They can sue you and say, hey, you didn't do the thing we did. It cost us money. You need to pay us money. But there's also even an element where if you don't comply with an expected standard, you potentially could be charged with criminal negligence. And that could be like $1 million fine or a multi-million-dollar fine, or it could even potentially be a prison sentence. But I like to say that generally engineers know when they're crossing that line. So in the other class, I went to quite exhaustive examples. But I'll give an example in a second when we talk about aviation, and I'll give an example then. Okay, so engineers typically rely on mathematics to make assumptions based on things like loads. And then they use their scientific understanding of things like materials. Like, so what do we know about concrete? Or what do we know about the flow of fluids? So how do we know how water is going to flow through this stormwater network? And we'll take into our assumptions on environmental conditions. Okay, designs are usually independently reviewed and verified by third parties to ensure that they're suitable. So I use the example of when I used to be a designer, that any design was always checked by, so a designer would do the work, their boss, so the head designer, would then sign off to say that they had checked the calculations and that they were happy. And then it would go to the head of the department who would also check that they were happy. Now, in addition to that, there would also be what they call an independent verification, which would be done in another separate firm. Ours used to be done in Brisbane. And another, not a separate firm, but for us it was a separate branch of the company where they would do independent verification to check that our work met the standard. Okay, communication is the third point. Now, engineers communicate in a number of ways. The most obvious one is drawings. Drawings usually form the basis of contracts in engineering. So that's usually what we expect when we say we're going to build this house. The drawing will be what we're specifying. There'll be words that go along with that, but the drawing is what says this is how big the thing needs to be, this is how much steel needs to go into it. In Australia, drawings should comply with AS 1100. Now, I would say that's more loose than the AS 5100. Like, people could say, hey, look, we're not complying with the AS 1100 here because of these reasons. But generally, it's a very good starting point because that way everyone knows that on a drawing, an engineering drawing in Australia, that every dimension is in millimeters unless it's specified otherwise. That's where we start. That's our starting point. There's a French movie where this is in fashion, not in engineering, where they scam a company by having all of the dimensions be in millimeters, not in centimeters, and they expected the dimensions to be in centimeters. Typically, I think in textiles, dimensions are given in centimeters, at least in Europe. Anyway, so we talked about drawing, and then we said, okay, so engineers often write reports that serve as legal documents in contracts and disputes. An important, so they could be an expert opinion, or they could be to communicate research that someone has undertaken. An important line of work is in preparing proposals. So if you want to win work, you have to hand in a proposal to the government to say, hey, we think that we're the best team to build this bridge. And that you have to, once you have the work, you then have to submit like a monthly report to say, this is how well we're doing, and keep people informed about how your project's going. Often these reports will be presented as a presentation. Like, and I say presentation, I mean like a PowerPoint presentation. Technical writers, they can be hired to explain how something works. So like they could, for instance, if you're designing a printer, you might hire a technical writer to write the manual. Engineering firms often hire communications managers, and they could be in charge of making sure that the company is communicating effectively to all stakeholders. So they might put ads in the paper, they might have display centers, they might do letterbox pamphlet drops, all sorts of different things. They might have advertising, they might have even press releases to the media, all sorts of different things that a communications manager might do. Okay, the last point is project managers. Okay, the majority of engineers don't focus on design. The majority of engineers, they work as managers, and they supervise things like the production, operation, or maintenance of engineering projects. So we'll start with site engineers. So site engineers are typically civil engineers, and they supervise the construction of infrastructure. So it could be like a bridge or a railway or a dam or a road or something like that. A council engineer, So they don't produce stuff very much. Well, they might, but they generally don't make it. What their main job is maintaining stuff. So they go and do a weekly inspection to check for potholes, and then they prioritize which potholes they're going to fix. They might still do new work, right? They might do production. So, for instance, if you've seen like Parks and Rec, like there'd be engineers who are in charge of designing the drainage for a new park. Or when I worked for a rural council, I worked on the upgrade for a swimming pool and a toilet block. That was I did some other. I also did, like, we replaced a bridge, and we replaced the water supply to the town. So that was a huge job, replacing the water supply. But the pool was a huge job as well. So these are things where the local engineer, they're looking for jobs, and they say, well, this is the budget we have. What is the next priority that we should do to upgrade and maintain our assets? Okay, so chemical engineers, they might be in charge of things like a refinery. So Sydney used to have 2 refineries. We now kind of operate on about half capacity on one of those refineries. So, for instance, one of my daughter's friends, her dad is a chemical engineer. He used to work at one of those refineries. He now works in water treatment. And I have met a couple of chemical engineers, and they tell me that they didn't struggle to get jobs, but there's not many people who do chemical engineering. So I try to give you an idea of my understanding of how many people are in different fields, to try and give you an idea of how well supported each of the different fields is. Okay, mechanical engineers, they supervise factory production, while others might be responsible for the maintenance of aircraft. Okay. So, generally mechanical engineers, if someone said to me they're a mechanical engineer, I would assume straight away that they worked in a factory, or that they maintained factory equipment. But if they told me they're an aeronautical engineer, I might assume that they work in an airport, and they might just be doing a daily inspection of different planes. That might be it. They might work in a design office, designing new aircraft. They might be working on new jet propulsion systems. But it's far more likely that they work at an airport and they just do regular maintenance. Management involves ensuring that the work is done safely and meets quality standards. It's also important that the work is done on time and on budget, or within budget. Okay, quality management is the process to ensure that standards are met. In civil engineering, this includes inspections to check reinforcement for a concrete structure. So this is a pretty important part of construction, is that before you pour the concrete, someone will come and have a look, and they'll check the steel to check that the steel matches the drawings. And if they see that, like, hey, there's only half as much steel as it says there should be. I did this job a couple of times when I worked for council. But these days, it's usually done by private companies. And that can be a conflict of interest. This is an ethical problem in Australia, that construction companies, because if they can say to you, hey, if you don't give me a good report, if you don't sign this off, I'm not going to hire you next time. So we've had a couple of cases of really important large structures failing their engineering standards later in their service life. And when we look back, we worry that maybe the inspectors weren't objective, and that they weren't, they allowed something to pass that shouldn't have. Okay, the other thing I'll say is occasionally, so when I worked in rail, at one point, I had before a procession. So a procession in rail is when you close down the trains and everyone has to take buses, and they're all really excited about taking buses. Yeah, I'm looking for nodding. You know, everyone knows that feeling. Then what happens is, while you close down the line, you then flood the site with like 1,000 people, right? You have everything planned, everything's ready, and then just everyone gets in and we all do it. And so it's all finished in 48 hours or something like that. The thing is, what you go and do is you spend weeks beforehand getting your site engineers to go and check to say, hey, we need these steel stanchions, and they need to go up in these locations. And you might send someone over to the factory to check that the stanchion that they've made is what you've ordered, because they might have put something in the wrong spot. And I'll tell you that if this is ever your job, I want you to do it like if you made a mistake, it would cost the company $100,000, because that's what it will cost if you make a mistake. You might say, hey, this piece of steel, it's only worth like $1,000. I mean, if it's wrong, what's the big deal? Well, the big deal is, if it's Easter Sunday, that steel company, they're not open, right? So if they've made a mistake and you didn't check it, if you sign off that it's all good when it's not all good, you're now going to have 1,000 people sitting there staring at you saying, it was your job to check that this was ready to go in. We now don't have a stanchion to put in place. We can't do any work, right? And so then you have to call up the company and beg them to come in and make you something specially, right? And then they're going to have to hire a transport company and beg them to come and bring it in specially. The point I'm saying is, do it for the first, 100 times you do an inspection, do it like there's $100,000 riding on it. Okay, so that's my advice to you. Now, with aerospace parts, they are really, or aeronautical parts, I guess, they are really expensive because every step must be carefully documented. So the example I'll give you is that aircraft, this is for commercial aircraft or for satellites and things. A part, like a screw could cost $100. The same screw at Bunnings might cost 5 cents, right? And the reason for that is because, well, first of all, there's someone who mines and produces the steel, and then there's a person who machines the steel, and then there's another person who heat treats the steel. And what you need to do is you need to provide documentation from each of those people saying, yes, I have mined and produced this steel correctly. And the next person says, I have machined this tool correctly. And the next person has to sign to say, I have heat treated this thing correctly. And you'll have those signatures. And you have to say that there is no way that the screw that is in that plastic bag has been replaced. It's been kept securely so that way you can track where that screw has been throughout its whole life. Because when this is where we talk about ethics and where people do go to jail, is if it's revealed, if someone has the video footage of you going to Bunnings and you looking at the old screw and the new screw and you just, buying a screw that matches, and then you going at the checkout and you're wiping the sweat off your brow as you buy this screw that, for 5 cents instead that should have cost $100. That's the sort of thing that when that plane crashes, I mean, you probably only go to jail for a year, which is not bad for a plane crash that might kill 300 people, but that's where they could probably get you for negligence, right? For criminal negligence, and you could actually go to jail. Generally, they're pretty good. And I like to say that as an engineer, usually when you're being negligent, you know that you were negligent. You know that you did something that was wrong. That's my experience as someone who worked very briefly in professional industry and since then has been a high school teacher who reads, books written by other people. Okay, so that's why they're expensive. Management includes procurement, resourcing, and risk. Procurement is generally what we call buying stuff, right? And making sure that the right stuff is on site. So when we talked about, making sure that that steel column, the stanchion that you needed is correct, right? Someone is in charge of buying all that stuff, getting it ready. There's another person who's in charge of resourcing, which is making sure that, hey, we need 15 electricians on the day and we need 22 track workers. So this is they're kind of like laborers who work on railway sites. That's what we need. You need to make sure that those people are there ready to go. That's what resourcing does. Risk is it's a specialty in engineering. So there are engineers who you can be a risk manager, and your job is just to identify risks and to run calculations on them. But that's another element of management. Environmental management involves ensuring that quality controls are in place. So a couple of obvious examples are when you drive onto a construction site, there's something called like a cattle grid. So sometimes if you're in the country, you might notice that when you go into a property, there's kind of a gap with a moat, and then there's like steel bars that you drive over. When you drive over, you hear the do-do-do-do-do-do as the tires go over. That's so that cows, they won't walk over that because they can't get their foot over that. It hurts them to put their foot onto the pieces of steel. But why we have those cattle grids in construction is that when we have a big messy truck, what we do is first let's say you're digging out 100 tons of dirt. What you'll do is you'll put the excavated spoil, you'll put that into the back of a truck. You're supposed to wash that truck down so that way dust doesn't go onto the road. And then it drives over a cattle grid, so that so all the dust on the side of the truck shakes off and stays on the site. You might have seen that construction sites near you, that they'll usually have a fence, or they should by law have a fence around them, and they'll usually have a plastic mesh on the outside. And again, that's to stop dirt from getting out onto the street. You might do similar things to stop dirt from getting into the waterway, because that that pollutes the waterway. So that's an example of the sort of things that environmental engineers might be in charge of. So that's the end of my my document on the skills of the professional engineer. I've set homework based on this, where I've asked you to summarize. I would ideally like you to come up with your own examples. If you have to use the examples I gave you, I can live with it, but I'd rather you give your own examples. So we're done.